Hello, welcome to our AI and Data channel. Today, we're diving deep into the world of feature engineering, a crucial aspect of building robust and accurate machine learning models. So, what exactly is feature engineering? Well, think of features as the building blocks of your dataset, and feature engineering as the process of creating, selecting, and transforming these features to improve model performance. Let's take a look at some examples across different domains. In finance, common features might include transaction volume, volatility indices, or historical stock prices. In retail, features could be customer demographics, purchase history, or seasonal trends. And in insurance, features might include policy details, claims history, or demographic information. But why is feature engineering so important? Let me illustrate with an example. Imagine you're building a model to predict customer churn for a subscription-based service. If you only have basic features like customer age and subscription length, your model might not capture all the nuances leading to churn. However, by engineering additional features like usage patterns, engagement metrics, or customer support interactions, you provide more context for the model to learn from, leading to better predictions. Now, let's talk about where feature engineering fits into the machine learning process. It's not a one-time task, but rather an iterative process intertwined with data pre-processing, model training, and evaluation. First, we start with raw data. Then we perform tasks like imputation for missing values, normalization, and scaling. After that comes feature engineering, where we create new features, transform existing ones, and select the most relevant ones. This is followed by model training, where these engineered features are used to train our machine learning algorithms. In the realm of feature engineering, several best practices stand out as guiding principles. One such practice involves tapping into domain expertise to craft features that truly capture the intricacies of the problem domain. By drawing upon a deep understanding of the subject matter, engineers can create features that are not only relevant but also insightful, leading to more robust and accurate models. Another critical aspect is handling missing data with care. Missing values are a common occurrence in real-world datasets, and how they are addressed can greatly influence model performance. By employing appropriate techniques such as imputation or exclusion, engineers can ensure that missing data does not compromise the integrity of the analysis. Feature leakage is another pitfall to watch out for. This occurs when information from the target variable inadvertently leaks into the features, leading to inflated model performance during training but poor performance when model is used for prediction. Vigilance is required to prevent feature leakage. Regularly evaluating feature importance is also crucial. Not all features are created equal, and some may have a more significant impact on model performance than others. By periodically assessing the importance of features, engineers can identify those that contribute most to predictive power and prioritize them accordingly. Lastly, it's essential to ensure that features remain relevant to the problem at hand throughout the machine learning process. As the problem evolves or new data becomes available, features that were once informative may lose their relevance. By staying attuned to changes in the problem domain and updating features accordingly, engineers can maintain the efficacy of their models over time. Let's delve into the key components of feature engineering. Data transformation involves manipulating raw data to either create new features or transform existing ones. Techniques include normalization, where features are scaled to a similar range to prevent dominance, logarithmic transformation for handling skewed distributions, and binning, which groups continuous values into discrete bins to capture nonlinear relationships. Feature generation entails creating new features based on domain knowledge or insights from exploratory data analysis. Techniques include generating polynomial features to capture nonlinear relationships and creating interaction terms by combining existing features to capture synergistic effects. Feature selection is about identifying the most relevant features to improve model performance and reduce dimensionality. Techniques include univariate feature selection, where each feature is evaluated independently, recursive feature elimination to iteratively remove the least important features, and feature importance ranking, which assesses each feature's contribution to predictive power. Feature table modeling involves structuring and organizing the dataset to facilitate feature engineering and model training. This includes defining the feature table schema, handling missing data through strategies like imputation or exclusion, encoding categorical variables into numerical representations suitable for machine learning algorithms, and managing feature interactions within the feature table. By mastering these technical components and strategically applying them, you can effectively engineer features that enhance the predictive power of your machine learning models. Lastly, let's talk about modeling feature tables. A feature table is essentially a structured representation of your dataset, where each row corresponds to an observation and each column corresponds to a feature. Modeling feature tables allows us to organize and manage our features efficiently, making it easier to apply transformations, perform feature selection, and feed the data into machine learning models. The benefits of feature tables include improved reproducibility, easier collaboration among team members, and better organization of the feature engineering process. To implement feature engineering effectively, you need a combination of technical skills and domain expertise. Technical skills include proficiency in programming languages like Python or R, familiarity with data manipulation libraries like Pandas, and knowledge of machine learning algorithms. In conclusion, feature engineering is a critical step in the machine learning pipeline with the power to significantly impact model performance. By understanding the domain, selecting and transforming features wisely, and following best practices, we can unleash the full potential of our machine learning models. Thank you for watching, and stay tuned for more insights into the exciting world of AI and data.